Welcome back to the Deep Dive. Today we're peeling back the layers on something invisible but totally essential, the infrastructure powering your digital life.
hmm
Think about it. AI tools you use, real-time analytics, even the future, autonomous vehicles.
Right.
Every single byte, every calculation, it relies on this silent engine,
Mm,
the modern data center.
absolutely. They're the hidden backbone.
So we're in this era of just extreme digital demand, and these data centers, they're kind of struggling to keep up.
They really are.
The core question we're diving into today is how do we scale them? Make them bigger, faster, cheaper, but still efficient? It sounds like a massive challenge.
It absolutely is. And the scale,
Yeah.
well, it's truly monumental. If you look at global capital spending for data center infrastructure, and this is excluding the IT gear itself,
Okay.
projections show we're likely going to exceed $1.7 trillion by 2030.
Wow, 1.7 trillion. That's huge.
Staggering. But here's the really interesting part, the opportunity. Smarter designs, better project delivery. They could potentially cut that massive number by up to $250 billion.
$250 billion saved just by building smarter.
Exactly. It's not just about building more. It's fundamentally rethinking how we design and construct them.
So that $250 billion figure,
Hmm.
is that mostly about like new tech or changing the process or just thinking differently? What's the biggest piece?
It's definitely a mix, but I'd say the biggest lever there is a fundamental shift in the project delivery mindset, moving away from these one-off builds.
Like custom everything.
Yeah, towards a more lean manufacturing style approach, especially in design and using modular components. The tech enables it, sure, but changing the process, building repeatably efficiently, that's where the huge savings come from.
That makes sense.
Yeah.
A crucial difference. So for you listening, this deep dive is your shortcut to understanding this massive shift.
Mm.
You'll find out what's fueling this crazy growth, the big hurdles the industry's facing, and the really cutting-edge solutions that are set to reshape how we literally build our digital world.
It's a fascinating time.
Okay, so what specifically is driving this almost bottomless appetite for data center capacity?
Well, there are a few key things piling on top of each other.
You mentioned three main drivers.
Yes.
on it.
First, you've got the massive needs of AI workloads, just enormous.
Okay, AI is number one.
Then there's the rapid spread of edge computing, bringing processing closer to where the data actually gets generated.
Right, edge computing. And the third,
Continuous advancements in high-performance computing,
Mm.
HPC.
HPC. Remind us, that's for the really heavy-duty calculations.
Exactly. Think complex scientific research, financial modeling, weather forecasting,
Okay.
stuff that needs incredible power and speed, handling huge, intricate calculations.
Got it. So it's everything from, like, streaming your favorite show in 4K to the algorithms behind medical discoveries. It all needs a home.
And a very powerful, very energy-hungry home at that.
So let's talk energy. The demands must be just off the charts.
Oh, they are. Truly staggering. Let's put some numbers on it. Global power demand for data centers expected to hit 1,400 terawatt hours by 2030.
1,400 terawatt hours. How big is that, really?
Well, to give you some perspective, that's about 4% of total global power demand.
4%, just for data centers.
Just for data centers. And what's fascinating, or maybe a bit scary, is how fast this is growing. Way beyond what anyone predicted even a few years back.
So the scale is escalating quickly.
Incredibly quickly. Before 2020, a typical facility might need, say, tens of megawatts. Now, we're talking hundreds of megawatts, even whole campuses needing a gigawatt or more.
A gigawatt scale.
Yeah, 1 gigawatt. And just look at the U.S. alone. They'll need to more than triple their data center power capacity in just the next 5 years or so.
Triple it.
Yep. From about 25 gigawatts demand this year, 2024, to over 80 gigawatts in 2030.
That 4% global demand figure, it's like powering a whole country, isn't it?
Pretty much. Roughly the entire energy use of Canada or Australia. It's a massive new draw on power grids.
Mind-boggling. And this gigawatt scale,
Yeah.
it's not just packing more servers in, right?
Yeah.
The physical size must be enormous.
Oh, absolutely. We're talking about a huge physical footprint.
Yeah.
These new facilities, they're often hybrids hosting AI training, inferencing, cloud workloads.
A mix of everything.
Exactly. And they're so vast, they're being designed on plots of land over 4 million square feet.
4 million square feet. That's hard to even picture.
It is. Meta's Louisiana campus is a good real-world example. Gives you a sense of the sheer physical space these things are consuming now.
Okay, so massive scale, massive power draw. How does efficiency fit in? You can't just keep using more power indefinitely.
You really can't. And that brings us to a critical metric, PUE, or power utilization efficiency.
PUE.
It's basically a ratio. Total energy going into the data center divided by the energy actually used by the IT equipment itself.
So lower is better.
Yeah.
Less waste.
Precisely. The industry is aiming for a really ambitious target now, a PUE as low as 1.1.
1.1. How does that compare to now?
It's a big improvement. Current industry averages are typically, somewhere between 1.5 and 1.7.
Getting down to 1.1 sounds incredibly difficult, especially with AI servers getting hotter.
It is incredibly tough because with AI server density shooting up, you're not just moving heat anymore, you're really fighting it. The key insight now is that it's often less about optimizing airflow and more about getting cooling right to the chip.
So that changes everything. Building design, material.
Completely. And achieving that low PUE isn't just about saving money on electricity, though that's part of it. It's crucial for maximizing the actual computing output while minimizing energy use and the environmental hit. Essential for sustainable growth.
Okay, so the demand is crystal clear. The need for scale is obvious. Why isn't everyone just building these bigger, faster, cheaper data centers right now? What's the holdup?
Well, it's because the traditional ways of doing things are basically hitting a wall.
The old methods aren't working anymore.
Not at this scale, no. Many developers still use what's called a stick build approach.
Stick build, meaning built on site, piece by piece.
Yeah, essentially. And often they'll put multiple repeatable data center buildings on one site, but each building gets its own independent backup systems generators, cooling, everything.
Okay, seems redundant.
It is redundant and inefficient at scale. Let me give you an example that really highlights it. A typical 30 to 60 megawatt data center might need, say, 8 to 15 diesel generators for backup.
Right, standard practice.
But if you just try and scale that approach up linearly to a 1 gigawatt campus, you'd theoretically need up to 290 generators.
290, that's absurd.
It really shows the inefficiency, right? It drives up costs massively, complexity goes through the roof, not just for the build, but for maintenance, managing power outages. The old way just doesn't work for the scale we need now.
Oh, 290 generators.
Oh, yeah.
Yeah, that paints a picture of a small power plant just for backup. So it's not just about building more, it's changing how we build.
Exactly.
And you mentioned 4 major roadblocks the industry has to overcome to really scale up properly.
That's right. 4 big ones. First, just securing enough power in the first place.
Okay, power availability.
Second, developing efficient and scalable cooling systems, absolutely critical with AI heat loads.
Cooling. Makes sense.
Third,
Addressing the very real skilled labor shortages.
right, finding the people to build these things.
And finally, navigating the ongoing supply chain instability, getting the actual equipment.
Okay, power, cooling, labor, supply chain. Let's maybe unpack those a bit. Power first.
Sure. The fundamental problem with power is that the traditional grids, well, they often just don't have the capacity for these huge facilities without massive, expensive, and very time-consuming upgrades.
So long delays just waiting for the utility company.
Exactly. Long delays, which
Yeah.
forces developers to look at alternatives.
Yeah.
We're seeing people explore behind-the-meter natural gas
It's
turbines.
generating power on site.
Yeah, or even dedicated nuclear plants, or the newer idea of small modular reactors, SMRs. SMRs, those mini nuclear reactors. That sounds futuristic.
It does. They promise consistent, carbon-free power, built in factories, deployed faster, potentially ideal for data centers.
But there's always a but.
But yeah.
Yeah.
Regulatory hurdles are huge. Public acceptance is still a question mark. And honestly, the timeline for SMRs becoming widely viable, certainly before 2030, it's still pretty uncertain. Big capital investment, too.
Okay, so power is a major bottleneck. What about cooling? You mentioned AI heat.
Right. AI servers just consume so much energy, they generate intense heat, often way more than traditional air cooling can handle.
So you need something more powerful.
Definitely. Advanced stuff like immersion cooling, where servers are literally submerged in liquid or other forms of liquid cooling, are becoming essential.
Immersion cooling.
Yeah. The tricky part is these technologies are evolving super fast. So for a developer building something meant to last decades, deciding which tech to bet on and when to integrate it, it's a really tough call, a big bet on the future.
Constant technological churn makes planning hard.
Mhm.
Got it. Then labor.
Labor's a big one. The industry is facing potential, sometimes already actual, shortages of skilled workers, especially during the peak construction phase of these mega projects.
When you need the most people on site.
Exactly. And high turnover, which often comes with shortages, impacts everything: safety, quality, and crucially, sticking to the project schedule.
And drives up costs.
For sure. Labor costs are expected to climb, partly because of the shortage itself, and partly because these huge new builds are often concentrated geographically. You might need thousands of workers on one site during peak construction, finding them, housing them. It strains local resources.
Yeah, coordinating thousands of specialized workers sounds like a logistical nightmare without new methods.
It really is. And finally, the supply chain.
Still feeling the effects of the pandemic.
Somewhat, yeah. Things have improved since the worst of it, but the supply chains simply haven't scaled up enough to meet this projected explosion in demand.
So, long waits for key components.
Still seeing long lead times for critical, specialized gear generators, switchgear, big transformers. And adding to the uncertainty, you've got new tariffs, export controls, potential trade spats.
More volatility.
Exactly. Which could easily lead to cost increases, maybe 5 to 10%, on really crucial equipment, especially in places like the U.S.
Okay, those are some pretty significant hurdles. Power, cooling, labor, supply chain. It sounds daunting.
It is.
But here's where it gets really interesting, right? Despite all these challenges, the experts are finding ways forward. It's about rethinking design, technology for the long haul.
That's the exciting part. There are clear pathways emerging.
And you mentioned 6 key focus areas that could really redefine how these things get built.
Yes, 6 main areas. We can probably group them into, say, 3 logical themes to make it easier to follow.
Okay, sounds good. What's the first theme?
The first group is all about intelligent design for mass production.
Mass production. Like manufacturing cars.
Kind of, yeah. Bringing that mindset. It starts with developing scalable reference designs with sequential phasing.
Okay, what does that mean exactly? Scalable reference designs.
It means moving away from totally custom, one-off designs for every single project. Instead, you create highly optimized blueprints that are maybe 60 to 80% standardized.
Standardized for efficiency.
Right, but still allowing maybe 20 to 40% customization for things that have to be site-specific, like foundations or grid connections.
Makes sense.
And these designs heavily feature things like modularization, building sections off-site, and consolidating all the complex mechanical, electrical, plumbing, the MEP systems.
The guts of the building.
Exactly. Consolidating those into auxiliary pre-built units. This whole approach is already working really well for build-to-suit projects or the big hyperscalers.
Okay, so standardization and modular design. What else in this group?
The second piece here is integrating an end-to-end delivery model and accelerating schedules.
End to end, connecting all the phases.
Precisely. Linking site selection, design, construction, all of it with really clear accountability throughout. And there's a cool innovation here, a generative scheduling tool.
Generative.
Yeah.
Like AI-driven scheduling.
Kind of, yeah. It uses a 4D model, that's a 3D architectural model, plus the dimension of time.
Okay, 3D plus time.
To run literally thousands of simulations of the project schedule and resource plan. It figures out the absolute optimal sequence for everything.
Finding efficiencies humans might miss.
Totally. And the potential payoff is huge. It could improve delivery schedules by as much as 20%.
20% faster construction. That's immense. What's the biggest bottleneck that kind of tool usually finds that, people overlook? Does it ever suggest weird counterintuitive stuff?
It often flags up unexpected dependencies, maybe between different construction trades or waiting on specific equipment deliveries. It shows how a seemingly logical build order actually creates hidden delays.
Ah, the ripple effects.
Exactly. And yes, it absolutely comes up with counterintuitive ideas. Like it might suggest delaying one task that seems critical on the surface.
Which sounds wrong.
Right. But delaying it slightly allows another maybe more complex task to happen in parallel. And that ultimately shaves weeks off the total project time. Stuff that goes against the usual construction wisdom.
Fascinating. Okay, so that's intelligent design. What's the second big group of solutions?
The second group is about reinventing the physical infrastructure itself.
Getting into the nuts and bolts.
Yeah. First, we need to rethink power, mechanical, and electrical systems at scale, including redundancy. We talked about the inefficiency of every building having its own backups.
The 290 generator problem.
Right. The solution for these gigawatt-scale campuses is a campus-level redundancy design.
Sharing the backups.
Essentially, yes. Integrating redundancy across all the critical systems and buildings for the whole site. This lets you make smarter, risk-based decisions about how much equipment you really need and where to put it, while still hitting those super high reliability targets, like the 5 nines uptime, 99.999% of a Tier 4 data center.
So, campus-level redundancy. It's like moving from every house having its own generator to a neighborhood having a shared, optimized emergency power station.
That's a great analogy, yes. Leveraging the scale of the whole campus to share resources much more intelligently.
Okay. What else in reinventing infrastructure?
Then we need to move beyond just using supplier-specific modular parts to integrating truly at-scale modules.
What's the difference? Aren't people already using prefab stuff?
They are, yeah. Prefab and modular components often make up 40 to 60% of the parts in modern data centers, even up to 80–85% for the real leaders. But often there's still just individual components delivered to the site for assembly in the traditional stick-build way.
So it's still assembly on site.
Right. The real innovation here is building much larger integrated sections, think entire rooms or functional units in dedicated fabrication yards.
Off-site factories.
Exactly. And then shipping these massive pre-built modules to the site as complete packages, like processing units or equipment skids. It's similar to how they build huge pre-assembled units for oil refineries or offshore platforms.
Pre-built modules arriving like giant Legos, ready to click together. That's a cool image.
It is.
But what are the big hurdles to making that common practice, logistically, engineering-wise?
The biggest challenges are probably standardization and transportation. First, making sure these huge modules are standardized enough so you can actually repeat the process across different projects and sites.
Making the Legos interchangeable.
Kind of, yeah. And second, just the sheer logistics of moving these massive, heavy, pre-integrated units from the factory, often over long distances, to sometimes pretty remote data center locations. That takes a whole new level of engineering, transport planning, specialized cranes, all that stuff.
Big shift in logistics.
Okay.
What's the third and final group of solutions?
The last group focuses on strategic technology bets and collaborative ecosystems.
Okay, tech bets and working together.
First part of that is to integrate scalable technologies into the design and make big bets on future cooling technologies. We keep coming back to cooling.
Because AI makes it so critical.
Exactly. The intense heat means advanced liquid cooling is basically non-negotiable for high-density racks. And there are three main types people are looking at now, each with pros and cons.
Right, the liquid cooling options.
Yeah. First, rear door heat exchangers, or RDHXs. They kind of combine air cooling with a liquid-cooled door on the back of the rack.
A hybrid approach.
Sort of. Good for maybe 40–60 kilowatts per rack. It's the most similar to traditional systems, so maybe easier to adopt initially.
Okay, RDHX. What's next?
Then you have direct-to-chip, or DTC technology. Here, liquid flows through pipes directly onto the hottest components, like the main processors.
Taking the cooling right to the source.
Exactly. This is probably the most popular approach right now. Handles higher densities like 120 kilowatts per rack, and sometimes you can even retrofit it into existing racks, offers a good balance.
DTC. Got it. And the third?
And the third is liquid immersion cooling. This is where you literally submerge the entire server into a special non-conductive dielectric fluid.
Dunking the servers.
Pretty much. This offers the highest cooling potential 100 kilowatts, even up to 150 kilowatts per rack with some variations. But it's the least common right now, requires a total rethink of the hardware and facility design. You see it sometimes in crypto mining.
Immersion, highest density, biggest change. So how do developers choose?
That's the million-dollar question, or maybe billion-dollar question. It's a trade-off. RDHX is easiest to integrate now. DTC tackles the hotspots directly and is adaptable. Immersion offers the ultimate density and efficiency, but needs a radical redesign.
So it's a big strategic bet.
It's a critical long-term bet. The choice affects the building design, the layout, operating costs, even what kind of computing workloads you can handle efficiently for the entire life of the data center.
Huge decision. Okay, what's the last focus area? You mentioned collaboration.
Yes, the final piece is to strategically enter collaborative contracting models with contractors and suppliers.
Bringing them in earlier.
Much earlier. Instead of just hiring contractors late in the game to build a finished design, you integrate them right from the start. During site selection, during design.
Leveraging their practical expertise.
Exactly. They know what's buildable, what materials are available, where potential problems lie. And you structure the contracts differently, sharing risks, but also sharing rewards.
Win-win incentives.
Right. Maybe tying incentives to hitting key operational milestones, not just finishing construction. This kind of partnership can save maybe 3 to 5% on capital costs per project.
That's significant.
It is. And importantly, it helps address those big pain points we talked about, the
Right.
tricky supply environment, finding good contractors, and the absolute need for speed in building these things out. It fosters real partnership.
Okay, so bringing all 6 of those together.
Yeah.
Standardized design, generative scheduling, campus redundancy, scale modules, smart cooling beds, and early collaboration. What's the overarching idea?
The overarching idea, the philosophy that ties it all together, is adopting a true lean manufacturing approach across the entire portfolio of data center projects.
Lean manufacturing for construction.
Yes. Not just isolated improvements on one project, but a systematic focus across the board on controlling costs and boosting performance. And that involves 3 key systems working together.
3 systems.
Yeah, first, the technical tools, like those digital twins we mentioned for simulating construction and operations. Second, robust management systems, clear processes, clear accountability. And third, maybe most important, the people systems.
People systems. Like culture.
Exactly. Culture shifts towards innovation, continuous improvement, even creating new specialized roles like dedicated blueprinting teams focused just on optimizing those reference designs. It's like taking the old measure twice, cut once idea to a whole new industrial digital level.
Wow. What an incredible deep dive. We've gone from the sheer scale of demand, driven by AI and edge, to the huge challenges of power, cooling, labor, supply chains, and now these really ingenious solutions that are emerging. It's a profound transformation happening right now.
It really is.
It feels like a race to redefine how we actually build the backbone of our digital future.
Absolutely. You know, the spread of these huge gigawatt-scale data centers, it really marks a significant leap forward in our global digital infrastructure.
A whole new era.
Definitely. And while the challenges are substantial, no doubt about that, especially with technology changing so fast, the opportunities for developers to scale up, get much better at project delivery, and actually meet this growing demand, they're immense.
So it's a critical time for innovation.
It's a critical moment for innovation, for strategic thinking. The decisions made now will really shape our digital world for decades to come.
Profoundly. Indeed. Which leaves us with a final thought, maybe. As we move towards this future powered by these unseen gigawatt-scale data centers hidden away, how might our own daily digital lives, our expectations for instant AI, for everything on demand, how might that continue to shape the actual land and resources around us? And what new innovations will that future demand from us next?
That's a great question to ponder.
Something to think about until our next deep dive.